Yes, thank you very much for having me here. And I'll talk you through, this is the last slide. I should start from this first one, I think. It could be a very brief talk if we do it this way. Thank you. I'll talk you through detector and physics studies that we have been doing for some time for linear E plus E minus colliders. Of course, part of the goal of this talk is to convince you of the benefits of a linear machine in comparison with other options. But I think there's also a large overlap in detector design. We've seen a lot of examples in physics studies, in development of tools. And I think having a communication between the different E plus E minus projects can only enhance our chances of convincing the HAB community as a whole, that is largely working on hadron colliders, as you know, that E plus E minus is an interesting thing to build. As a disclaimer, this talk is a personal view. It doesn't reflect the position of all the projects I'm involved in, nor do the positions of all those projects necessarily agree. And an acknowledgement, the work I'm showing, the material I'm using in this talk is, of course, the result of a lot of work by a lot of people, especially the core development of detector designs, Monte Carlo tools, etc., is absolutely vital for any of this to happen. Let's start from where we are now. Particle physics at the energy frontier is, of course, dominated by the LHC, and we have LHC for another while. The high Lumi phase will take us to 2037, which is close to retirement age for some of us. But we shouldn't be complacent, right? That doesn't mean that we should just sit and wait and let it run, let the machine do the work. We need, I think, a plan for the future very soon now. The longer-term future may include hadron colliders of different flavors, a 27 TeV energy doubler in the same tunnel, or a brand new hadron collider with a center of mass energy of up to 100 TeV. I won't discuss those, but of course, the whole thing is interrelated, and what happens there will affect us to some extent. Even going a bit further back, I use this slide to get some urgency behind that claim that we need a decision, right? The first LHC workshops were a very long time ago. The LHC was formally approved in the mid-90s. I think the decision by the CERN Council to go ahead was in '94. We started in 2010, of course. If you then project that whole stage into the future, you see that we need to decide more or less now to get anything running by the end of operation of the current collider. And I think we need that. We can't have a gap between the high Lumi LHC and the next project of 15 years without a lot of talented people just leaving the field. Linear colliders, of course, are based on R&D in cavities. There's much more to it, but cavities are the key element. To give you a perspective again, the SLC was built with 17 megavolts per meters. That ran at the end of the last century. We've made some progress, but it would have been nicer to have a factor 10 than a factor 2 here. So, ILC cavities can now do 35 megavolts per meter. You've seen the XFEL operating at 30, so that's definitely doable. And a lot of the R&D that's now happening is not going into getting a bit more gradient, but it's making these things cheaper, easier to build, more reliable, etc. You need these things to be very mature to be able to propose a project on them. CLIC has higher gradient with warm cavities. Daniel has gone through all that in a bit more detail than I can. The concept of that is proven in large-scale tests. Plasma wake field has come up this morning, that in a vision of linear colliders into the end of the century, that could take over when CLIC runs out of steam. Of course, Daniel has given you more information. These are links to two talks that I think give a very nice perspective of where all this could be going. Then This plot has been shown. There are many different versions of it. Of course, we're not arguing about 9T GeV. There, the best machine is a circular one. We're not arguing about 3TV either. There, linear is the only thing you can do. And in this region, things are a bit more delicate, and that's the region where things are likely to happen. Now, rather than discussing the potential of the machines based on this plot, I think we should take into account polarization options of different machines, realistic scenarios, normalized in time, and then do the physics studies and compare after we've done that. But clearly there is a complementarity between linear and circular machines. So to set the stage, I think you're mostly aware of this. ILC has defined operating scenarios a few years ago. 2 inverse attobarn at 250, 4 inverse attobarn at 500, and a bit of luminosity at the top threshold. Now, a 20-year program going to lower and higher energy, having some upgrades, could give you all this. Positron polarization is in for the ILC, 30%, and electron beams are polarized to about 80%. We share the luminosity according to this key here. So all that has been worked out in a lot of detail, and this is the program we think gives us the best physics return quickest. Now, you've heard already, negotiations to get the project started have required us to go to a project with a starting date and end date that focuses entirely on the 250 GeV operation. We've redone the physics case to some extent, 2 inverse attobarn. Of course, there are losses there, right? We lose a lot of top physics. Vector boson fusion is done worse, but this was a necessary step to make sure the ILC could be approved by Japan. I'm not sure if it's a sufficient step, but it's a necessary step. The committees that are important in this field have reacted favorably. SSJA had the Japanese high energy physics. They have a committee on future projects. They say we should start in Japan immediately without delay. ICFA, the International Committee for Funding Agencies, again, makes the right statements. Now it's up to Japan to give us the one statement that matters. CLIC, on the other hand, has gone a slightly different route. Daniel has already told you it's 3TV operation. That is sort of the focal point. We assume that some new physics will tell us that's where we need to run. Of course, there's flexibility in exactly the center of mass energy that you can run at. And the initial stage is at 380 GeV. It's an interesting value. It does have some top physics. It has Higgs physics. You can do vector boson fusion better than you can at 250. It is a bit of a compromise, but it is a point that gives us a broad program in a single run of limited duration. So we think this is an optimal way to start a project. Again, as we learn, maybe new discoveries will tell us how to adapt this. So detector R&D. This is already ongoing. A lot of the talks this morning have had a lot of inspiration from ILC and CLIC detector design, detector R&D studies. I'll show you some highlights. Emilia Leogrande has a longer talk about tracking, and I think a lot of the developments that have been done in the ILC and CLIC have already made their way. So a few highlights. The next generation of pixel detectors, we've heard about CMOS, and these are no longer nice IDs that have a proof of principle detector of the size of a stamp in a beam somewhere. Right? There is a real vertex detector in STAR based on CMOS sensors from Strasbourg. Mu2 3E is basing its design on it. Alice is betting heavily on CMOS. Even Atlas is considering CMOS for the upgrade. So these are proven technologies. We know we can build detectors. A new technology to join that category is now DepFET, depleted field effect transistors. Bell 2's vertex detector that is in construction as we speak is based on this technology. There are also applications in X-ray imaging. And this image actually has both. A plume ladder is based on CMOS. The depth ladders are shown here. This is BEAS 2, the commissioning detector of Bell 2. Bell has a history of burning holes in vertex detector. So we want to go in with a small prototype that measures the beam environment, the background levels very precisely before we come with the real thing. There are other technologies, fine pixel CCDs, silicon on insulator. They're a bit behind. They're not yet at the level where they've built a detector and shown that it can be transformed into a system, but they're quite mature and they meet most of the linear collider requirements, probably also the CEPC requirements. Of course, the big difference there is power consumption. ILC and CLIC can use the duty cycle of the machine to save a lot of power. I think CEPC needs a lot more work on getting the cooling to take out the power, and of course bringing the power in with little material. High-speed readout is developed for the LHC to some extent, for CLIC. Hybrid pixel detectors, I wouldn't discard them yet. They are getting much thinner, and especially if you keep the radiation resilience requirements low, you can build pretty thin hybrid detectors. So CLIC is pursuing this to some extent. Depleted CMOS can be quite fast. This is something that Alice is actively pursuing, and I think would be very interesting for CEPC. 3D integrated devices, they're a big promise, but they've been so for a while, so we'll see how that evolves. 4D tracking, this has come up. Timing precision in position-sensitive detectors is feasible. There's something we call a low-gain avalanche detector that collects the signal very quickly. And then if you have the right electronics on top of it, you can get a 50, 20, even 10 picosecond time resolution for your hits. There's always a price. You never get anything for free in this world, so there is a price in power consumption to be paid, probably. Slightly more recently, people have inverted the ALGAT and put the amplifying layer on the opposite side, which is very beneficial in terms of gain uniformity. And to feed into that discussion that we had in one of the previous talks, this is good for particle ID. Of course, particle ID is very good from time of flight at low energy. DEDX is somewhat complementary to that. Combining the two, this is a slide from Manchi at the Linear Collider workshop, but it was worked on in the CEPC studies. This can yield a very good separation, and it is important. We have a lot of physics cases where we use kaons to understand whether a B was a B or a B bar jet, et cetera, et cetera. So there are very good arguments for this. Highly granular calorimetry, this is of course one of the success stories of linear collider detector R&D. Callies has done realistic prototypes of quite sizable dimensions for the electromagnetic part, for the ironic part, and then you can use a combination of measurements in test beams in Monte Carlo to predict the performance of a complete calorimeter. Now the nominal 21% over square root of E that you could get with perfect particle flow is somewhat reduced. And in practice, we're closer to 3% constant jet energy resolution as a function of energy than to the 30% over square root of E. And that's because there's a confusion term, right? Even with this granularity, even in a clean environment, there is confusion between particles, and that starts kicking in at higher energy. So that makes the curve flatter than you would have hoped. Again, they're beyond just proving that a small scale prototype can work. They're doing integration in a quite industrial manner. This is a pick and place machine that integrates the scintillator on the readout electronics. They have calibration schemes that use the fact that you can identify MIPS inside showers, and you can calibrate the detector all the time with that. And one major step towards maturity of highly granular calorimetry is the adoption of CMS, of this concept for their forward system. Again, that will oblige Callies and people involved to go through the full chain of everything, not just the prototype in a test beam. Detector design and performance studies then. Of course, there are detailed detector designs. They're informed by this detector R&D, so we know what's feasible and what's not to some extent from having tried it out in test beams. These concepts were optimized quite carefully and repeatedly for benchmark performance. So we've gone through some physics analyses and repeated them with smaller, larger detectors, smaller and larger B fields, etc. This is all extensively documented for the TDRs, and it's still ongoing. Basically, we have 3 prototypes: the ILD large detector. It's a combination of silicon and a TPC. SID is more compact, higher field, all silicon tracking, and up some of the design to being able to cope with 3 TeV operation. So it's a deeper calorimetry. The forward region and the vertex detector have to be adapted to make sure they will deal with the background levels at click. Timing has to be stepped up, of course. So this, I think, was a proof that you can quite easily pick up one of these designs, port it to a slightly different environment, re-optimize, and then start developing further. And now, actually, the click group is one of the drivers for studies of detector design. We're, of course, ready for CPC, and that has happened already to a large extent, to adopt these, to adapt them, and to improve what we did. Detector performance studies. It's a large effort. It's been a large effort to set this all up. I don't think it would be possible to do it now. We had a lot of manpower on ILC and click, of course, in the past, and we're still getting the benefits from that. There are core software packages like LCIO for persistency. It's a lot of work to set it up, and it's vital to have something that works very well for all the studies to follow. Geometry, this is more recent. DD4 HAP is now implemented fully in the ILC and click detectors, and I think already some other projects are adopting it as well. RICO framework with Marlin, grid submission, you need all these things to be able to study anything. Also, there's been a lot of work into high-level reconstruction algorithms. Of course, if your detector is very good, but then you don't know what to do with all that information, you underestimate performance very dramatically. We have pretty performant LCFI vertex and flavor tagging algorithms. Pandora PFA, I think, is the state of the art. There is a second attempt to get PFA running, and it's important to see what the limitations of Pandora are, how you could improve on that. And the second algorithm will help identify those areas. There's a bit of work on jet reconstruction. Again, all these things have to be rethought for high energy plus-minus colliders. Can't just take what was available from that. Then detector optimization. Of course, we need a complex multi-parameter optimization in that case. We have the benchmark studies that tell us what the requirements are, but again, as detector R&D progresses, we find that some things that weren't feasible 20 years ago may be feasible today. So it's a continuously updating system. Costing studies, of course, will tell us at some level what's feasible as well. If physics studies require a bigger and bigger detector, at some point costing will come in and limit that. And of course, it's always better to be more granular, to be more precise, but there are kinks like these. So this is the jet energy resolution as a function of detector granularity, if you want, expressed in terms of the number of channels. So clearly it doesn't matter whether we put 70 million or 20 million channels in this calorimeter, but it does matter whether we drop below 10.7 or so. So we try to identify these edges and to stay on the safe side of them. Again, all this has been extensively documented for you to take advantage of. The physics potential then. I don't think I have to convince you that precision physics is much better done at the plus-minus colliders. The LHC will be more precise than we had envisaged the Hadron Collider could be maybe 10 years ago. But still, it's a different level. Of course, we know this, the machine, we know the energy, the luminosity, etc., the polarization, if it's available, to 10 to the -3 level typically. We can select events without modeling through orders of magnitude of QCD processes. We don't even need a trigger for most of the things we do. The detector can be designed for performance rather than for surviving pileup or radiation damage. And the theory becomes easier, and it can reach better precision. No PDFs to be taken into account to first order. QCD corrections are typically very small, so we can get a few per mil level cross-section predictions already today with no dedicated effort going into these calculations. As an example, take the top quark pair production cross-section. 5% is a major achievement at the LHC. It's very hard to see how we gain a factor of 2 on that. But you can do 5 per mil at the linear collider already today, basically. Another thing from theory I need, and I think this is a development that we should take advantage of, is effective field theory is being more and more used in LHC interpretation. We can consider the LHC a low energy machine, if you pardon my insult there. But, and then we assume the high energy new physics to be out of direct reach, but we can get sensitivity to it from precision measurements. So we express the Lagrangian as the standard model one, plus a whole series of higher dimensional operators that represent some kind of new physics. If you do this, taking into account all 59 Wilson coefficients, you have a pretty general description of what might be out there. The main assumption is it's compatible with the symmetries of the standard model, and it has a scale that's beyond the direct reach. But otherwise, there are very few assumptions in that. So this is a very economic way of doing interpretations. We can measure things, report the result in terms of limits on these coefficients, and then the theorist can go and map it onto their favorite model, which doesn't have to exist yet at the time of the measurement. It allows to connect measurements in different sectors. We can connect measurements in Higgs with electroweak physics, etc. There are standards being drawn up by the LHC physics working groups, and the linear colliders jumped on this and done some pretty pioneering studies for Higgs couplings, electroweak precision, WW production, etc. in this framework. And it really is, the ILC or CLIC are machines that can do this very well. Let's go very quickly through the physics highlights. This is, of course, the art from run 1, Higgs couplings. The recoil mass analysis, I'm sure you're aware of this, is a gold mine for doing these coupling measurements. You can go to the couplings that we think ought to be there for a standard model Higgs boson. This is the EFT study I've talked to you about. You can do pretty stringent limits on the visible decays. We lack dedicated analyses of Higgs to tau mu, to name just one. CLIC, as I said, 380 is a bit different. You get a bit of vector Bose fusion and Higgs Strahlung at the same energy. This gives very competitive results at 380. Of course, adding the high energy operation only improves that. The Higgs self-coupling, this is one of the reasons why high energy and energy extendability of a collider is important. Higgs self-coupling is very hard to access at any machine. I think probably the best bet at getting there is a high energy linear collider. You have to run above 500 GeV if possible. There's a bit of a plateau between 500 GeV and a couple of TeV, but you can get to a measurement of 10%. And this is an important parameter. It could have large deviations, and if they do, it's definitely a sign that the Higgs mechanism is not standard. Same thing, top Yukawa, the LHC can do it to about 10% precision. ILC or click, depending on the choices of center of mass energy and integrated luminosity, can get 2, 3, 4%. The FCC-HH target is 1%. I'll go through this quickly, this one as well. Top physics then, I'll focus on the standard stuff. The top mass you've seen from Roberto, we can get to about 50 MeV. And there, it doesn't matter whether you're RLC or click or CEPC. It's mostly the systematics that dominates that precision. Top electroweak couplings, we've done a very detailed study of this. This is the 500 GeV result for the CP conserving interactions. These are the CP violating interactions. Now, if you try to think of what is the right center of mass energy to do these measurements, the result is that you need both high energy and low energy operation. There are a number of effective operators that are very well done at low energy, where the cross-section is larger. There are others where the sensitivity grows so strongly with energy that even a less precise measurement at high energy is much more constraining. This is now being worked out. We're trying to do an as global as possible fit, 7 parameters so far, of all the operators that affect top electroweak couplings. Results are really, really very promising. You can get to the 10 to the minus 3, 10 to the minus 4 level. There's no way we can get anywhere near that at the Hadron Collider. In terms of sensitivity to concrete new physics, I'm wrapping up. You probe out to 20, 30 TeV. So really these have the potential to answer questions about what lies beyond the standard model or to discover new physics. I'll leave the summary for you to read. Sorry for running over time, and I'm happy to take some questions.
Thank you. Thank you, Marcel. There are questions?
So you were spending several slides on AFTs and their advantages, which there are indeed several, but I wondered, could you connect C9 from the B physics observables to any of these?
No, it's not so easy. I tried to answer this question in a workshop in Madrid a couple of weeks ago, and it's not obvious. So the operator itself is hard to extrapolate to energy frontier machines. And if you go to the concrete models, you can easily write a model where some of those violations of lepton flavor universality are not affecting the electrons, right? You could easily have all the new physics in the coupling to the muons, and then the E plus and minus machines are out of the game. You have to build a muon collider. But again, we don't know what new physics this is. There isn't a single one of those models that looks very convincing per se. So I think unless we make some progress in understanding what it is, it's very hard to extrapolate to energy frontier colliders in general and E plus and minus machines in particular. Yeah.
Yes.
I have one question about the justification of this machine respect to the circular collider, right? Because as you said, this is very nice in thinking to a possible extension, right? Making a 3 TeV collider or waiting for plasma acceleration that we can do in linear collider, but not in circular collider. But if I think at the target with 215 GeV machine, the precision that it seems that you can reach is not far from high luminosity LHC. Maybe it's the same, is a factor 2 better, maybe 3, let's say, right? While if you go to a circular collider, you go factor 10. And the cost of this machine is not far from a circular collider. So my point again is if I had to choose one machine between the two, why should I choose this one to make a Higgs factory? So this is my...
Right. It's very hard, despite all the work, to compare the Higgs coupling precisions directly, right? There are at least 3 ways of interpreting them. There's the kappas from the LHC, there's EFT, and there's the model independent fit that we've done. I think we should carefully do the comparison of CEPC the ILC click to see exactly which machine is more promising, taking into account the limitations from theory, etc. So I'm not going into the numbers there. But yes, my preference for a linear collider comes from the fact that you can extend it into energy. So you can make, rather than getting stuck at some energy like lab was maybe, you can think of a program where 250 GeV is just the first step of a long-term future, which maybe even you and I won't be able to take advantage of in our active lives, but we'll all live to be 120, we'll see it, right? And I think that is the power of a linear collider. You can rip out the 250 GeV machine or extend it, make it 500, then go to a TeV. Hopefully plasma wake field acceleration comes, and at some point you have a program that can last a century. Now that's not what Japan wants to propose, right? They want a project with a starting date and an end date. I think that's probably true even for a project at CERN. But I think that's the benefit of linear colliders over circular colliders.
Okay, I can make a little comment on that. I think we need to understand that point better, because nobody has actually a design that is even near working for a linear collider above 3 TeV. And I think there's real reasons for that. There's at some energy, the synchrotron radiation in the final focus quadrupoles will keep you from focusing the beam. And so there are lots of things which need to be ironed out before one goes, and I can do a plasma wave accelerator at 30 TeV. That isn't something that actually works.
Right. I think if you want to discuss concrete proposals with a costing, etc., 3 TeV is where we can go.
You know, the click at 3 TeV is almost the same price as the Hadron Collider of 100 TeV. So we don't, you know, within a factor 50% or something.
Yeah, I haven't seen the
so
numbers
we have to,
for the...
Exactly, you haven't seen those numbers.
You haven't either officially, have you?
No, but I've been asking for them.
All right.
I think we need to sit down and carefully assess those arguments.
Right. I think
they are useful. As far as the Higgs, well, you know, what you find in the particle data book are branching ratios and partial width. And that's what we need to measure. And we need to measure them model independently. So that's what E plus E minus machines can do. I think the comparison, what we need to compare is fairly straightforward.
Yeah, I think for the concrete proposals on the table, it's easy enough to work out the physics potential. And it's been done to a large extent. Except that it's been done by a different group with different assumptions sometimes, but yes.
Okay, yes, Imad, and then I think we should have lunch because we are going to eat each other otherwise.
Yeah, I have a few comments, but short comments. First of all, I think the extension to up to 1 TeV, which is, I mean, we are defending this scenario for the linear collider. It's also very important for the Higgs self-coupling possibility, okay? And I think it's an important point. That, I mean, we cannot do it for the circular collider at this energy, even up to 380. Now, I want to make a comment on your talk. You showed some slides saying that we have a limitation for the granularity. Frankly speaking, I think that for PFA-based detectors, the higher the granularity you have, the better. But you have two limitations from the detector point of view, okay? And this we can understand. We can have other detectors, but also the PFA algorithm you are using. Because if you have a smarter one, I'm quite sure that you can exploit this granularity for the PFA-based. For other technology, I don't discuss. But I think we didn't invest enough power and manpower to work on this. And I think next step is really to go in this direction.
Right, I agree. It's a very subtle business, optimizing a detector. First, you have to pick the figure of merit, right? And that's already up to discussion often. And then if you have a very sophisticated detector design and rather poor reconstruction software, you'll be measuring the limitations of the software rather than of the hardware. And yes, we've been struggling with that for 20 years, I guess, and I don't think that you can trust a single parameter optimization ever, but through doing this multiple times, you learn where the kinks are, where the limitations are. And as you do detector R&D, you learn what the limitations from there are. In the end, you come to a design that can be built, has the performance, and is cheaper than the machine.
Okay. Let's thank Marcel again, and thank you for all the speakers this morning.